December 1942. While London's streets still bore the scars of the Blitz and U-boats strangled Britain's Atlantic lifelines, a peculiar convoy arrived at a nondescript warehouse in Birmingham. Inside, 14,700 tons of pure silver, borrowed from the Bank of England's reserves, not for currency, not for trade, for something the enemy could never imagine. British scientists needed the most conductive material on Earth to build electromagnetic separators capable of isolating uranium-235. Copper was rationed for ammunition, so they borrowed a nation's silver wealth and turned it into atomic fire. Within 3 years, they'd cracked the atom itself and changed warfare forever. 3:47 a.m., 18th March, 1940. Oxford's Clarendon Laboratory, its Gothic windows rattling from distant air raid sirens across the Thames Valley. Professor James Chadwick, 48, discoverer of the neutron 8 years prior, stood over scattered papers covered in calculations that refused to reconcile. The tea beside him had gone cold hours ago, a cardinal sin in peacetime, but these were not peaceful times. Outside, searchlights swept the clouds, hunting for Luftwaffe bombers that came with mechanical regularity. The strategic situation was catastrophic. France would fall within months. The British Expeditionary Force faced annihilation at Dunkirk. German U-boats had sunk 374,000 tons of Allied shipping in 3 months alone, threatening starvation. Wehrmacht divisions were massing across the Channel, awaiting invasion orders. Britain stood alone against a military machine that had conquered continental Europe in 18 months. Conventional warfare was failing with mathematical certainty, but Chadwick understood something the generals did not. Physics had revealed a theoretical weapon of such devastating power that a single bomb might obliterate an entire city. The problem was uranium-235. Natural uranium contained only 0.7% of this fissile isotope mixed with 99.3% inert uranium-238. Separating them required technology that didn't exist. The Germans knew this too, and German scientists like Heisenberg had discovered fission simultaneously. Intelligence reports suggested Nazi Germany had commandeered Norwegian heavy water plants and Czech uranium mines. The race was already underway, and Britain was losing. Chadwick's colleague, Dr. Rudolf Peierls, burst through the laboratory door without knocking. The 33-year-old German Jewish refugee who'd fled the Reich in 1933 carried a folder marked "Most Secret." His hands shook, not from fear, but exhaustion. "James, we've recalculated. The critical mass isn't tons. It's kilograms, perhaps as little as 5 kilograms of pure uranium-235. The implication detonated silently in Chadwick's mind. An atomic bomb wasn't theoretical. It was achievable. And if Britain didn't build it first, Hitler would. Within weeks, the Maud Committee, named cryptically after a misunderstood telegram, assembled Britain's finest scientific minds: Chadwick, Peierls, Otto Frisch, Francis Simon, and a dozen others, many refugees from fascism who understood exactly what Nazi victory meant. Their mandate was impossible: determine if an atomic bomb was feasible, and if so, how to build it before Germany. They faced immediate obstacles that would have crushed lesser men. Britain's industrial capacity was stretched to breaking. Every factory was producing Spitfires, tanks, ammunition, ships. Steel was rationed, copper was sacred, needed for shell casings, electrical wiring, telecommunications. Aluminum went to aircraft frames. Rubber was nearly unavailable. How do you build revolutionary technology when you can barely feed your population? The Maud Committee's calculations were brutally precise. Separating uranium-235 required electromagnetic separation using massive cyclotrons called calutrons. These machines needed thousands of miles of electrical windings made from the most conductive material available. Copper was the standard choice. But every pound of copper diverted to atomic research meant fewer bullets for soldiers fighting in North Africa, fewer shells for naval guns protecting convoys, fewer electrical systems for radar stations defending the coast. Francis Simon, the German-born physical chemist who'd fled Berlin in 1933, proposed the unthinkable during a December 1940 meeting in a cramped Whitehall basement. The minutes recorded his words precisely. "If copper cannot be spared, we must use silver. Pure silver is more conductive than copper. The Bank of England has it. We borrow it." The suggestion was met with stunned silence. Borrow 14,700 tons of the nation's silver reserves, worth approximately 70 million, to wind electrical coils? The Treasury representatives present looked physically ill. Britain's currency was backed by these reserves. In wartime, perception of economic stability was nearly as important as actual military capacity. Rumours of depleted silver reserves could trigger financial panic, weaken the pound, undermine international credit. But Chadwick understood what the Treasury men did not. If Germany developed atomic weapons first, silver reserves would be irrelevant. There would be no Britain to defend. The meeting adjourned at 2:30 a.m. with a provisional decision pending cabinet approval. Chadwick walked home through blackout-darkened streets, past sandbagged buildings and Morrison shelters, under skies that still smelled of smoke from previous raids. Somewhere in those skies, German reconnaissance aircraft photographed Britain's defences. Somewhere in occupied Europe, German scientists worked on the same problem. The race had begun, and Britain had just wagered its national treasure on physics most people couldn't comprehend and technology that had never been built. 3 days later, Churchill's War Cabinet approved the requisition with a single-sentence authorization: proceed with utmost urgency and secrecy. The silver would be borrowed, the atom would be split, or Britain would cease to exist trying. 7th of January 1941, 5:15 a.m. Birmingham, a city still clearing rubble from November's devastating raids that killed 2,241 civilians and destroyed entire neighborhoods. The Metropolitan Vickers Electrical Engineering Works operated behind blast walls and camouflage netting, its chimneys cold to avoid attracting bombers. Inside, Chief Engineer Harold Wilson, 54, stared at specifications that violated every principle of his 40-year career. The silver had arrived via guarded railway convoy over 3 weeks, each ingot stamped with Bank of England hallmarks, each shipment logged with obsessive precision. Not stolen, borrowed. The Treasury demanded its return after the war, every ounce accounted for. Wilson's team had been given a task that sounded like industrial poetry but felt like controlled chaos. Melt 14,700 tons of silver, draw it into 13,540 miles of wire, enough to stretch from London to Sydney, and wind it into electromagnetic coils that had never been manufactured at this scale. The technical challenges were staggering. Silver melts at 961.88 degrees C. The furnaces required coal that was rationed for steel production. The drawing machinery needed precision tooling that normally took months to calibrate. The insulation materials, enamel coatings to prevent short circuits, were in desperately short supply because chemical plants were producing explosives instead. And the timeline was impossible. Complete installation within 18 months, while German bombers attacked Birmingham's industrial heart every 48 hours on average. Wilson's workforce was a patchwork reflection of Britain's total war mobilization. Skilled metalworkers in their 50s, too old for combat, but possessing irreplaceable expertise. Women machinists who'd trained for 6 months to replace men fighting overseas, now operating lathes and presses with concentration that defied their exhaustion. Polish refugees who'd escaped Warsaw's destruction and would work until collapse rather than see another city burn. Teenagers barely 16, apprenticed in trade schools that now taught wartime improvisation instead of peacetime perfection. They worked in conditions that peacetime safety regulations would have condemned. The factory operated under blackout conditions, windows painted over, lighting minimal to prevent silhouettes visible to aircraft. Temperatures inside the furnace rooms exceeded 40 degrees Celsius, but ventilation was limited because it created heat signatures visible to infrared detection. Workers rotated through 4-hour shifts, longer ones causing mistakes from fatigue that could ruin weeks of work. The first crisis came on 23rd of January, when a bombing raid destroyed the primary cooling water system. Electromagnetic coils generate tremendous heat. The silver windings needed constant cooling or the insulation would melt, causing catastrophic short circuits. With no municipal water pressure, Wilson's team improvised a system using reclaimed rainwater stored in bomb-proof cisterns and pumped manually during air raids when electrical systems shut down. It reduced capacity by 40%, but prevented total failure. The second crisis was material science under battlefield conditions. The electromagnetic separators, called calutrons, after the University of California, where the design originated, required vacuum chambers with tolerances measured in microns. Any air leakage would contaminate the uranium isotope stream. British manufacturers had never built vacuum vessels at this scale. The welding techniques needed were experimental. Leaks were discovered through painstaking testing, each one requiring disassembly, repair, and recalibration that consumed days. Dr. Mark Oliphant, the Australian physicist coordinating between scientists and engineers, became the project's troubleshooter. He slept 4 hours nightly, shuttling between Birmingham factories, Cambridge laboratories, and Whitehall meetings, where he fought bureaucrats for every resource. His reports documented the grinding reality. 12th February, delivery of insulation materials delayed 14 days due to convoy losses. 19th of February, 3 skilled electricians conscripted for military service, irreplaceable expertise lost. 3rd March, furnace malfunction, 8 hours production lost, silver reclamation required. The workers developed coping mechanisms that revealed national character. During air raids, rather than fleeing to shelters, essential personnel remained at posts maintaining furnace temperatures and monitoring cooling systems. They joked grimly about Jerry's interruptions and bet cigarette rations on whether bombers would target the docks or factories. A Spitfire pilot photograph was pinned to the factory wall with the caption, "He keeps them off, we keep working." Churchill visited once, unannounced, in April 1941. He toured the floor, where silver wire spooled onto coil forms, watched molten metal pour into casting molds, spoke briefly with a grandmother operating a precision lathe. To Wilson, he said only, "The nation's treasure is in your hands, not just the silver." Then he departed, leaving workers who suddenly understood they weren't just manufacturing components. They were forging the weapon that might determine whether their children grew up free or enslaved. By August 1941, the first complete calutron stood assembled in a laboratory outside Oxford, its silver coils gleaming under industrial lighting. The electromagnetic field strength measured 1.4 Tesla. Sufficient, theoretically, to separate uranium isotopes. The machine consumed 250 kilowatts, enough to power a small town, but Britain's overstretched electrical grid somehow provided it. The testing phase revealed the final challenge: consistency. Uranium hexafluoride gas, fed through the separation chamber, behaved unpredictably. Isotope yields varied between 3% and 11% purity when the requirement was 80% plus. Something in the process was introducing variability that calculations hadn't predicted. Teams worked through September analyzing magnetic field patterns, gas flow dynamics, temperature fluctuations. The breakthrough came from an unexpected source. A Scottish engineer named McGregor, 62, who'd spent 30 years in shipyard electrical systems, noticed the calutron's performance correlated with barometric pressure. Atmospheric pressure affected the vacuum chamber's stability, which altered gas density, which changed isotope separation efficiency. The solution was counterintuitive. Don't fight the variation, compensate for it. Automatic pressure regulators, calibrated to weather forecasting, adjusted the electromagnetic field strength in real time. By December 1941, the first gram of 85% pure uranium-235 had been separated. It had required 14,700 tons of borrowed silver, 18 months of continuous work, bombing raids that killed 14 workers, and innovations that wouldn't be published in scientific journals for another decade. The atom hadn't split yet. But the tools to split it now existed, built by ordinary people doing extraordinary work in the shadow of potential annihilation. 2nd December 1942, Berlin. Wehrmacht, High Command Intelligence Briefing Room, where maps of the Eastern Front competed for wall space with industrial production charts. Oberst Heinrich Müller, head of scientific intelligence, delivered a report to senior officers that combined certainty and confusion in equal measure. Allied atomic research has accelerated significantly, Müller stated, referencing decoded communications intercepts and agent reports. American uranium procurement from Belgian Congo mines has tripled. Canadian heavy water production is confirmed. But, gentlemen, we have a perplexing anomaly. British silver reserves have decreased by approximately 14,000 tons since January 1941, transferred from Bank of England vaults to undisclosed locations. We have no explanation for this movement. The officers dismissed it. Currency manipulation, perhaps? Economic stabilization measures? Britain's finances were chaotic. They were bribing neutral nations, financing resistance movements, subsidizing Soviet war production. Silver movements were the least of their concerns. The Reich's atomic program, under Heisenberg's leadership, had determined that atomic bombs required tons of uranium-235, making them impractical wartime weapons. Germany's limited resources were better spent on rockets, jets, and submarine technology that could actually win the war. This assumption, that atomic weapons were theoretically possible but practically unachievable, was the strategic blinder that would cost Germany everything. By mid-1943, the British-American atomic collaboration was producing results that German intelligence couldn't fully comprehend because they contradicted established German calculations. The Oak Ridge facility in Tennessee, using Calitron designs based on British research and wound with American silver borrowed from the US Treasury, was separating uranium-235 at scales Heisenberg had declared impossible. The critical mass wasn't tons, it was kilograms, and those kilograms were being produced gram by gram, through electromagnetic separation powered by silver that enemy intelligence had tracked but never understood. British scientists, meanwhile, operated with an advantage born of desperation rather than superior theory. They had been forced to innovate under resource constraints that German scientists, backed by an industrial empire spanning Europe, never experienced. When copper was unavailable, they used silver. When precision instruments were destroyed in bombing raids, they built alternatives from salvaged parts. When theoretical models failed to match experimental results, they trusted experiments over theory, a pragmatic empiricism that faster produced practical weapons. Professor Chadwick traveled to Los Alamos in December 1943 as head of the British mission, bringing with him data from 2 years of British research. The Americans had industrial capacity Britain lacked, but British scientists had solved fundamental problems American researchers were still attempting. The relationship was complementary. British innovation meeting American production. German intelligence intercepted fragmentary communications about Site Y in New Mexico and increased activity at Oak Ridge. They knew something significant was occurring. But Heisenberg's theoretical framework, accepted as gospel by German scientific establishment, insisted that atomic weapons remained years or decades from realization. Allied efforts, they concluded, were either bluffing or pursuing a dead end that would waste resources better spent elsewhere. This arrogance was institutionalized. When young German physicists suggested alternative separation methods, they were overruled by senior scientists protecting their reputations. When intelligence reports indicated anomalous Allied industrial activities, Wehrmacht planners assumed it was deception to mask conventional weapons programs. The rigid hierarchy that Germany prided itself on, decisive leadership, clear chain of command, deference to expertise, became a liability when that expertise was fundamentally wrong. By contrast, British scientists operated in an environment where desperation forced open-mindedness. Churchill demanded results, not theoretical purity. Engineers collaborated directly with physicists, bypassing academic hierarchies. Failure was acceptable if lessons were learned. Complacency was not. This cultural difference, pragmatism versus orthodoxy, manifested in technical choices that compounded over time. June 1944. While Allied forces landed in Normandy, Los Alamos scientists achieved the first successful implosion test of a plutonium core. British scientists contributed critical explosive lens designs that compressed the core uniformly, a problem American researchers had struggled with for months. The silver-wound calatrons continued producing enriched uranium. Two paths to an atomic bomb were now confirmed: uranium-235 gun-type design and plutonium-239 implosion design. German intelligence received reports of massive explosions in the New Mexico desert in July 1945. They attributed them to conventional explosive testing for rockets or strategic bombing munitions. The idea that a single weapon could destroy a city remained, in German assessment, science fiction. On 6th of August 1945, Hiroshima ceased to exist in a 15-kiloton explosion. The Japanese city's population of 350,000 was reduced by 80,000 instantly, with another 60,000 dying from radiation effects over subsequent months. 3 days later, Nagasaki suffered the same fate. Japan surrendered within 5 days. In Germany, now occupied and divided, captured Nazi scientists reviewed Allied atomic research reports with expressions of genuine shock. Heisenberg himself would claim the Allies must have exaggerated the bomb's power, that German calculations had been correct, that given time, the Reich would have developed similar weapons. These claims were self-serving delusions. German atomic research never came close. They had the theoretical knowledge, but lacked the industrial desperation that forced British innovation and the production capacity that American involvement provided. The silver had been the key, not because it was magical, but because borrowing it represented a national commitment that Germany never made. Britain wagered its financial reserves on an unproven technology because invasion was imminent and conventional warfare was failing. That desperation bred creativity, urgency, and willingness to attempt the impossible. Germany, confident in its military superiority, never felt that desperation until too late. 15th August 1945. London celebrated VJ Day with crowds filling Trafalgar Square, strangers embracing, church bells ringing for the first time since 1939. The war was over. Britain had survived, battered, exhausted, financially ruined, but free. In quiet offices across Whitehall, however, civil servants confronted a peculiar accounting problem. 14,700 tons of borrowed silver needed to be returned to the Bank of England. The recovery operation took 3 years. Electromagnetic coils were carefully unwound. Silver wire was melted and recast into ingots. Each ounce was weighed and logged. The final accounting, completed in 1948, showed a discrepancy of 0.036%, approximately 5.3 tons, lost to industrial process wastage, well within contractual tolerances. The Treasury accepted the return, and Britain's silver reserves were quietly restored. Most of the nation never knew their monetary foundation had been temporarily converted into atomic weapon components. But the true reckoning extended far beyond financial ledgers. The Manhattan Project, including British contributions, had cost approximately $2 billion, equivalent to $30 billion today, and employed 130,000 people across multiple countries. It had produced two bombs that killed between 140,000 and 200,000 people and ended history's deadliest war within days. The moral calculus was debated immediately and remains contested 80 years later. Were atomic bombings necessary to force Japanese surrender, or were they demonstrations of superpower intimidation as the Cold War began? British scientists who participated carried that weight forever. Chadwick, awarded the U.S. Medal for Merit in 1946, became an advocate for international atomic energy control, recognizing that Britain's contribution to atomic weapons had unleashed technology that threatened human extinction. Piles returned to academia, working on theoretical physics while quietly advising on nuclear disarmament. Many British scientists joined the Pugwash conferences, international forums seeking to prevent nuclear war. The silver itself became symbolic. In 1947, a Labour MP questioned in Parliament why Britain had helped develop atomic weapons when the technology was immediately monopolised by America. The answer was complex. British scientific contribution had been essential, but Britain lacked the industrial capacity to build bombs independently. American production facilities, including Oak Ridge's Calutrons, had used American silver borrowed from the U.S. Treasury, creating parallel but separate programs. Britain had provided the initial breakthrough calculations, the theoretical frameworks, and key engineering solutions, but ended the war without its own atomic weapons. This technological dependence became painfully clear as the Cold War began. America and the Soviet Union emerged as superpowers with atomic arsenals. Britain, victorious but bankrupted, was relegated to secondary status. The 1946 McMahon Act, American legislation restricting atomic technology sharing, effectively ended British-American collaboration despite wartime partnership. Britain would eventually develop its own atomic weapons in 1952, but at enormous cost to a nation struggling to rebuild from 6 years of total war. Yet the legacy of Britain's silver-funded atomic contribution extended beyond weapons. The electromagnetic separation techniques developed for uranium enrichment were adapted for medical isotope production, cancer treatments, and nuclear medicine. The industrial processes pioneered under wartime pressure became foundations for peaceful nuclear power generation. The collaborative model, scientists from multiple nations working toward common goals, influenced post-war international scientific cooperation, from CERN to the Human Genome Project. More subtly, the project validated something essential about British national character that defined the war effort: the capacity to wager everything on unconventional solutions when conventional approaches failed. Borrowing a nation's silver reserves to build experimental weapons was a decision that balanced on the edge of madness and brilliance. It succeeded because British scientists and engineers combined theoretical excellence with practical improvisation, refusing to accept that resource limitations made the impossible actually impossible. The workers who wound those silver coils mostly returned to ordinary lives. Harold Wilson retired from Metropolitan Vickers in 1948, his contribution to atomic weapons development remaining classified until the 1960s. The machinists, electricians, and engineers who fabricated components through air raids and exhaustion received no public recognition because the project's full scope remained secret. When documents were finally declassified decades later, historians pieced together their stories. Ordinary people who manufactured extraordinary technology while death fell from the sky. The atomic age had begun in university laboratories with elegant equations, but it was built in factory floors with borrowed silver and desperate determination. Britain's contribution, often overshadowed by American industrial might, was the spark that proved atomic weapons were achievable, not theoretical curiosities, but practical devices that could be manufactured within realistic timeframes. As the 1940s ended, the silver sat again in Bank of England vaults, indistinguishable from silver that had never left. But it had travelled to the edge of physics, been wound into coils that separated atoms, powered machines that changed warfare forever. A nation had borrowed its monetary foundation and transformed it temporarily into humanity's most destructive achievement. The atom had been split, the war had been won, and the silver, returned to its quiet storage, carried no visible evidence of the fire it had created. But those who knew its journey understood a fundamental truth. When survival demanded the impossible, Britain had wagered its treasure and won. Not through magic or miracles, but through the determination to attempt what others deemed impractical, to innovate when resources failed, and to trust that human ingenuity could overcome any obstacle when the alternative was extinction. That legacy, the willingness to risk everything on unconventional solutions, remains Britain's enduring contribution to the atomic age. The silver was just metal. The courage to borrow it was what split the atom. If this story of British ingenuity and determination moved you, subscribe to our channel for more untold stories from the Second World War. What other secret contributions changed history? Share your thoughts in the comments below. Did your family work in wartime factories? We'd love to hear their stories. Ring the notification bell so you never miss our next deep dive into the extraordinary efforts of ordinary Britons who helped win the war. Thank you for watching.